Hey, I'm Bryan, and this is a quickie version of the HVAC School podcast. And today we're talking about Delta T. Delta T, not Mr. T. Don't get the two confused. I pity the fool who gets the two confused. Sorry. And so we're talking Delta T today, which is not to be confused with temperature rise on a furnace. It's not to be confused with TD. No, those are different things. But before we get into Delta T, I want to thank our sponsors. Our sponsors are RectorSeal, Carrier, and Mitsubishi Comfort. And just want to remind you that RectorSeal makes two brands that I'm sure you've seen, which is the Safe T-Switch condensate overflow switch, the SS1, SS2, SS3. I use those. Been using those for years. Very reliable condensate switch. It's just our go-to. We haven't had any problems with them. They're a great product. And then also the AquaGuard product is part of the RectorSeal family. They make some pretty interesting products, especially for like ductless systems and for RTUs and that sort of thing. Some more interesting and unique products. They have one that you can actually unthread the bottom of the AquaGuard float switch and actually allow the water to be removed that way. So the interesting products. But today we're here to talk about Delta T. And so Delta T is often called, in fact, I never called it Delta T when I first started in the business. I used to call it a air temperature split or a temperature split. We would say, what's your temperature split? And the idea in our market was that it should be around a 20-degree split in cooling, which means that your return air coming over the evaporator coil, so the air entering the evaporator coil, should be about 20 degrees warmer than the air leaving the supply coming out of the top of the unit. And I would hear this all the time. Well, there's a couple challenges here, and I just want to point out a couple of the obvious ones. The first one is that you have to measure with your probes, good quality air probes, out of the line of sight of various surface temperatures, because otherwise you'll have radiant cooling or heating effect, in this case a cooling effect, where if you put it in line of sight of the evaporator coil, so that way if you imagine you're putting your probe in and that probe is in the direct line of sight of that coil, say in a case coil above a furnace, it will drop the surface temperature of that probe and it will give you a incorrectly low temperature in that supply. And the same thing's true if you were putting it, say, in a filter door on a fan coil where it was exposed to the bottom side of an evaporator coil. Whenever you expose a probe to line of sight, and I don't know a different way to explain that. I'm trying to think of a better way to explain it other than line of sight, but it's, if you can imagine, like they're directly exposed to one another through an air gap, they'll exchange heat by way of radiant heat transfer, and that will affect your reading. Like I said, it's got to be a good temperature probe. It can't be affected by significantly different temperatures. And then also it has to be in a reliable airstream. So if you think of a case coil on a furnace and you take a supply probe and you stick it in a portion of the coil that may have a lot of turbulence in it, or it may be in a part of the duct where there's not a really reliable airstream and it may be affected by the wall temperature of the duct, then you may not get a really good measurement. So generally speaking, you want to be a little bit downstream of the coil as much as you can reasonably get. So what I generally do in our marketplace, we have a lot of fan coils, and you get those kind of turbulence coming out the top, and sometimes you won't get a really good reading right off the top of the unit. I'll bring it up maybe 2 feet or as high as I can get it away from the unit in order to take the measurement. Once it's had a chance to mix a little bit, it's a little bit more accurate. And then it also, on a case coil, it tends to get you away from the coil a little bit, so you're not going to be as affected by that radiant heat transfer. One thing when you're measuring a Delta T, don't use a infrared thermometer. Don't use something that you're shooting with a laser. It's just not going to be accurate. They measure surface temperatures, not air temperatures. I see home inspectors do this a lot when they'll walk through the house and they'll shoot a return and they'll shoot a supply and they don't read a proper air temperature split that way. And also, when you do it inside the home, you're also taking into account any duct gains in between the system and the distribution point, in addition to the fact that you're reading the surface and not the air. So there's just all sorts of challenges there. Not to say that it's a completely useless measurement. It's just not, you can't use the typical rules for Delta T that we talk about. The next thing that people get wrong with Delta T is they get this idea that it's a fixed number, that you can say a 20-degree Delta T no matter the conditions. Well, Delta T does have, it's not a straight line. There's actually a curve to it, and it's related to the enthalpy in the air. And enthalpy is overall heat content. We also have enthalpy in the air from the heat of vaporization in the water, latent heat of vaporization. And that means that it takes quite a bit of energy to take water vapor and change it to liquid water, which is something that we do when we cool the air. As long as that evaporator coil is hitting dew point, we're going to pull moisture out of that air, and that affects the delta T quite significantly. And so you can't just say, I should have a 20-degree delta T. That delta T can range anywhere from 14 degrees in some extreme cases, high airflow, all the way up to cases where your target could be 24-degree delta T. Based on that would be a case where you have low relative humidity air, so low enthalpy from moisture in the air, and then lower airflow. So you're going to see this range there. And so even when you look at something like a delta T target chart, which we have on HVACrschool.com, if you go to the resources page, we have a delta T calculator there, which is a good tool to get you in the ballpark. Even with that calculator, it's using the generally accepted 400 CFM per ton for cooling for that calculator. So if you have a case where you're running lower than that or higher than that, well, then that also changes the equation. And some of you may know this, but in southern climates, or not just southern, but high humidity climates, we often will run below 400 CFM per ton in order to remove more latent heat, which is, produce more moisture on the evaporator coil, remove more moisture out of the air. And in areas that are very dry, arid, or high altitudes, we can run up to 500, sometimes even 550 CFM per ton, but generally more in the 450 range. And that will also change your delta T. So let's talk about what affects delta T, because this is practical. So anything that reduces equipment capacity can also reduce delta T, but that's not the only thing. So having high airflow can also reduce delta T as well, or having high or higher than normal relative humidities in the return airstream. So high relative humidities can cause a low delta T. Low capacity, which is, there's an enormous list of things that can cause low capacity. Compressors not pumping properly, undercharge, overcharge, expansion valve issues. There's all kinds of different challenges that can cause low capacity. And then also high airflow. So if a system is producing more than its target airflow, then that will also reduce the delta T. And again, delta T is just the difference between air coming in the return and air going out the supply. So what can cause a high delta T? Well, the first and most obvious is low airflow. So if you run into a system that has a higher than target delta T, that's usually the first place I'm going to look. And often that can be something as simple as a dirty filter, dirty coil, but it can also be the way this equipment is set up. It could be producing significantly less than 400 CFM per ton. That may be what you want it to do. So in that case, you don't necessarily change that. But in some cases, that may not be what you want it to do. An example of a designed time in which you'll run a higher delta T than what you would normally anticipate would be a case when a system is running in dehumidification mode, where it's intentionally ramping down that blower in order to pull more moisture out of the air, to run a colder, lower dew point evaporator coil. That's what happens in dehumidification mode, and a lot of controls in modern variable speed blowers will do that in residential, and you'll also see it in certain commercial applications. So that's a reason why you would see a high delta T, and that's one of the main reasons. You'll also see it if you have abnormally dry air. So the drier the air is, that's also the higher delta T that you'll have. That's basically it for this episode. Just wanted to give you a quick introduction to delta T. Don't use just a static measurement. Make sure you put your probes in the right places, in places where the air has a chance to mix and not line of sight to cold surfaces. Use good quality probes. Don't use cheapy little, I see some people still using the old dial probes. It's going to be tough to get an accurate measurement with that. I talk all the time about how much I like the Testo 605i. That's sort of my tool of choice for this purpose, not just of delta T, but to do delivered capacity and a lot of other things you can do with those tools. So that's my tool of choice. If you want to see our kind of generic calculator, you can go to the resource tab on HVACrschool.com. You may not know this, but the great communicator Ronald Reagan, before he was president, he was actually an air conditioning sales trainer.
We can outproduce, outcompete, and outsell anybody anywhere in the world.
Thanks for listening. We'll talk next time on the HVAC School Podcast.